I mean, these two cancel out, obviously. Okay? And if you multiply this p theta into this parentheses, okay, this one, it becomes p theta minus p theta prime. P theta minus p theta minus 1, right? Okay, so that's, you know, because everyone has a z as denominator, and 0.5, okay, there. So, okay, once you get these two out of the equation, the first one has a p theta minus 1, okay? And the second one, you get this one out, you get this one out. You are going to have like a plus p theta, okay, minus p theta minus 1. And then you get this one out, you get this one out. And then you have plus p theta, right? So, well, then you can see that, okay, we actually add 2p theta. We also add 2p, these two cancel out. Okay, so it's going to be z is going to give you this term, right? Okay, so the other one, the second case, okay, the second case, I mean, do you mind I erase this? Okay, should be very easy, right? The second case is that, okay, your p theta is the largest one. I mean, both p theta minus 1 and the p theta plus 1 are smaller than p theta. Okay, so we can plug in this into this formula. Okay, and again, you can see, because p theta is larger than p theta minus 1, so this term becomes larger than 1. So we will only take 1 here. So it's going to be p theta minus 1, 0.5 times z, theta plus 1. Oh, sorry, minus 1. And then plus p theta divided by z, and times the here, okay, 0.5 times 1 minus, okay, and we know p theta is the largest term. So we know this one is going to give us a smaller than 1 value. So we are going to take this, okay? So p theta minus 1, right? So we are going to take this. And then, okay, plus, again, this one is going to be a value smaller than 1. So we are going to take this one again as well. So plus 0.5 times 1 minus p theta plus 1. Okay? And then, okay, the last term, okay, plus p theta plus 1 divided by z times 0.5 times this one, okay, again, because p theta is larger than p theta plus 1, so this term is going to end up with to be larger than 1, so we are going to take 1, so just 1. Okay, so let's try to simplify this. Again, you know, we can put this thing in this into the you know, this parenthesis, and that means we cancel all this. This one becomes p theta. Same thing. This one we cancel all this. This one becomes p theta. Okay, and we get like a z and the z 0.5 out of here. So the first term we have p theta minus 1. Okay, and then the second one, okay, we get this one out. We get this one out. So plus p of theta minus p of theta minus 1 plus p of theta minus p of theta plus 1. Okay, and then, okay, the last term we get plus p of theta plus 1. Okay, so well, this one cancel each other. This one cancel each other. So we are going to end up with 2 p of theta. So, you know, the result is going to be, you know, p of theta divided by z. Okay, you can try to, you know, put in all these. I mean, any of these 4 cases. Okay, and you are always going to end up with, you know, p of theta divided by z. What does that mean? What does that mean? Here, okay, we are trying to put, okay, you know, we put this w into as like the probability of the location where the partition will be at each island. Okay, and it will give you, you see, at the ith turn, at the rth turn actually, I mean, it's going to give you p of theta divided by z. So you see, originally, okay, you put p of theta divided by z as the probability where it is going to end up at the island theta, and at the end, it tells you that, okay, the probability for, I mean after one iteration will stay the same, right? Regardless the relationship between different islands, I mean the neighboring island, obviously, between the neighboring island. Okay, as long as your probability at each island look like that. Okay, I mean, if you try to multiply this matrix, okay, meaning you try to expand for one more step, it's going to go back to the original term, right? That means what? That means it's this means like this probability distribution. This probability distribution. Okay, remember the p, p theta minus 1, p theta plus 1, blah blah blah. This basically means the population at each island, right? The population at each island, or you can say it's like the posterior distribution value at each location, whatever you call it. Okay, and why do we need to add a divided by z? Because we want to normalize it. The z is normalizing term, by the way. Okay, so this derivation basically tells us that this W, okay, or this probability distribution, okay, like this, is a stabilizing vector, okay, meaning V multiply this matrix, let's call that matrix M, it's going to be V again, right? Okay, V, let me repeat, V times this matrix is going to be V again. So basically, it's stabilized, okay, meaning we know like no matter where we start, the distribution will diffuse and explore other locations. But, okay, we know, okay, there will be some stable state. There will be some stable, and we have shown that this target distribution, the target distribution is a stable state, right? Right? So, so this is important. This tells you that, it is very likely, okay, after repeatedly applying this matrix, okay, eventually you are going to end up with this target distribution, okay? But, okay, why, if you remember, I keep telling you guys that, okay, yeah, this is I would say it's a kind of an argument instead of a proof, right? I didn't say this is exactly a proof, right? Why am I saying that? Okay, because okay, we know, yeah, applying this matrix, repeatedly, is going to end up. I mean, it's likely going to end up at a stable state. Yeah, we know that. But we cannot be sure. We know target distribution is one stable state. Okay, as I already showed you, right? But we didn't show that there's only one stable state, right? You may have more than one stable state, right? So mathematically, this is not exactly a proof. This is just an argument to tell you that, okay, this diffusion process, okay, eventually, okay, it's going to end up at some stable state. And this target distribution happened to be one of the stable states. But, in all this derivation, I didn't show you there's only one such stable state. So I cannot say this is a proof. Okay? But this is something I can give you that's closest to a proof. If you want to see a more, formal proof, okay, than this, okay, then remember I told you, okay, there's the German's textbook that you can refer to, okay. That one, okay, will talk about this whole thing in a much more rigorous mathematics manner, okay. But in computer science, I hope like you guys is satisfied with this argument, okay. So this algorithm, okay, is best known as Metropolis algorithm, okay. Why is it called Metropolis algorithm? Okay, the Metropolis refers to the papers, the author of the paper that proposed this algorithm. Okay, actually the first author. I mean, his last name happened to be Metropolis. If you know like English, you will know Metropolis means like big city. Okay, but no. This in here, okay, this really just means somebody's name. Okay, it just happened to be. I mean, his name happened to be Metropolis, yeah, this has nothing to do. Okay, this algorithm has nothing to do with big city. Okay, and to be honest, okay. The reason, okay, to be the first author, okay, this guy to be a first author is really not because he's that good, okay, because it's really because his advisor is really good, okay. His advisor is actually the mastermind behind this algorithm, but he got lucky because he found a good advisor. I mean, when they published a paper, his advisor put him as a first author. Some advisor will put a student as first author, some advisor will not. If the result is significant, okay, some professors will prefer to put his own name as the first author. But it happens that this Metropolis, his advisor is very nice, so he put his students as to be the first author, and so he got lucky. Okay, so his name is recognized. I mean, as like a name of an algorithm. Okay, so it tells you that, I mean, it's important to find a good advisor. Okay, yeah, just kidding. Yeah, okay, so yeah, so this whole derivation. Okay, well, it takes some time. So yeah, it's about time to take a 10 minutes break. When we come back, we are going to discuss like a more general Metropolis algorithm. Okay?